lecture, I am going to introduce another special type of two species interacting model, that is known as Gause model. This Gause model mainly fits with prey-predator interaction with specialist predator. So, most general format for the Gause type prey-predator model is dn dt, this is equal to n fn minus gn into p, where n is the prey population density at time t and p is the predator population density at time t. And then growth rate of predator population is described by dp dt equal to e of gnp minus some qp multiplied with p. So, in the absence of predator population, so that means if we assume predator is absent, this equation will not be coming into the picture, we can ignore this term. So, then single species prey growth is described by this equation. And as we have discussed during my third lecture in this series, then you can understand that Fn is the per capita growth rate of prey population. Similarly, this Gn is actually describes the grazing pattern of prey by their specialist predator. Now, the question is that why this predator is known as specialist predator? This is the intrinsic death rate or density dependent death rate for predator population. It is a positive function of p. So, if we remove prey from the system, then immediately we can prove that pt will be approaching to 0, they will not be able to survive. So, survival or existence of predator population is completely depending upon its only available food source, that is prey population n. It do not have any other resource based upon which it can survive. So, that is why it is called a specialist predator, and this E is known as the conversion efficiency, and its numerical value always lies between this limit 0 and 1. So, it means the growth rate of predator population is solely due to the contribution from the prey population due to predation. So, in this case, as a particular situation that qp equal to constant, if you consider qp equal to constant, so that means the linear death rate. So, therefore, this equation can be visualized as dp dt equal to some function of n multiplied by p. So, that can be considered in a crude manner that it is a exponential growth model for predator population, but its growth rate depends upon prey population. And as this is going to be a function of n and n is bounded, we can prove mathematically that n is bounded. So, therefore, this predator population never goes to explore. So, I am not going to show you the mathematical details, but for this type of model we can easily prove 2-3 different assumptions. Number one, if we start from a positive initial condition, solutions should remain positive at all time t. So, that is first restriction for the population dynamics models. Rather, we can say that if you have a model and which fails to satisfy this kind of positivity condition, then we cannot say this is a feasible model for prey predator interaction or population dynamics, because it is required to be assured that population should be positive at all time. But there are some exceptions, because in case of constant rate harvesting model we cannot prove the positivity. This is only for the reason that okay, within a finite time period resource can go to extinction or harvested species can be facing some extinction scenario if your harvesting effort is much larger compared to the available resources. So this is the standard Gause type prey-predator model, and very important and well known model is Rosenwick-McArthur model. This Rosenwick-McArthur model is defined by dn dt, this is equal to Rn into 1 minus n by k minus a np divided by b plus n, and dp dt, this is equal to E A n p divided by b plus n minus mp. So if we compare this coupled nonlinear ODE with the general format, easily you can check that Fn is going to be R into 1 minus n by k, Gn is equal to A n by b plus n, and Qp, just for simplicity you are assuming a constant m, and therefore this equation can be written as dp dt equal to p multiplied by some function of n. Now this particular functional format, that is Gn is equal to A n by b plus n, this is actually called Holling type 2 functional response. Holling type 2 functional response. Now the question is that from where or with which kind of assumption we derive this kind of functional response. Now I will give you the derivation that rate of predation by the predator follows this particular functional response. It can be derived. So in order to derive this functional response, first of all we need to define 4 different quantities. Number 1, n is the available prey. For the time being we can consider this is the number of prey. Then capital T is the total time. Total time means once predator are going for predation, they spend time for 3 types of activities. Number 1, searching for prey. Number 2, chasing or capturing the prey. And number 3, handling the prey. Right. So here we denote that T is the total time and TH, this is handling time for each prey items. So that means predator needs TH time to handle one prey. Finally, V denotes the number of victims. So that means number of prey caught by the predator. So once we define these 4 quantities, we can make an assumption. What is the assumption? That number of victims is proportional to the abundance of prey population, right? And also number of victims is proportional to the time they have for searching the prey item. The idea is that if there is no time for searching, so they will not be able to caught a single prey. So TH is the handling time for handling one prey by the predators. V is the total number of prey caught. So that means total time they have spent to catch V number of prey will be TH into V. right. So therefore, the time available for searching the prey is given by T minus Th into V, correct, and as per assumption V equal to alpha times this into N, correct. V is proportional to the prey abundance, V is proportional to the searching time, so V equal to alpha times this into this, where alpha is the variation constant, and from here you can derive that V equal to alpha Tn divided by 1 plus alpha Th into N. Right. So if you divide both numerator and denominator by alpha Th with different parameterization, you will be having this Holing type 2 functional response, that is A n by B plus n. There are some other functional response also, that is Holing type 3, Holing type 4. Mechanistically we can derive all these functional responses. At the end I will be introducing Holing type 3 functional response also, but at that particular functional response it is assumed that this alpha proportionality constant, this also depends upon the available prey density. So once you assume that this alpha is also proportional to that available prey density, or total time as well as handling time, they are also, there are two different opinions. This total time and handling time, they are proportional to the number of prey available there. So that means they are also proportional to n. So then this term will be modified by n square, and accordingly you will be having Holing type 3 functional response as some alpha n square by beta square plus n square instead of this one. Now once we derive this functional response, then next question is that what are the basic properties are satisfied by this particular functional response. In order to understand the basic properties, you can just draw a rough sketch for this function Gn against n. In this axis, vertical axis, you can plot Gn. So plot of this function is this one. This is a typical plot. Actual slope, then height of the asymptote, everything will be determined by the particular choices of A and B. Now you can see that at n equal to 0, this is 0. If you calculate the derivative of Gn with respect to n, you can find that G dot n is always positive. So that means this function is monotone increasing, and also it satisfies that it is monotone increasing but not unbounded above, rather it is bounded above, because for this function if you calculate the limit as n tends to plus infinity, you can find this is equal to constant, right. So if we divide both numerator and denominator by n and then take n tends to infinity, then you will be having A as the limit, right. So we can say that this A somehow is the saturation level for the predation, and if you choose n equal to B, then this quantity will be equal to A by 2, and that is why in some of the book you can find the interpretation for B as half saturation constant. In some literature you can find that they have mentioned that this B is the half saturation constant. Why? Because saturation level is A, right. So if you substitute n equal to B, this becomes A by 2, so exactly half of the saturation level, so that is why B is called half saturation constant. So these are the basic properties satisfied by this functional response, right. Now we need to analyze this model. To analyze this model, just from sake of brevity, I am not showing you the non-dimensional scheme, but I can directly go to the non-dimensional version for this model, and that can be considered as dx dt. This is x into 1 minus x minus xy by alpha plus x, and dy dt, this is equal to beta xy by alpha plus x minus delta y. Now quickly I can give you one important observation, that we have started with a model, there are some parameters, all the parameters are positive, and in the dimensionless version we have 3 parameters. So this is clear that we have reduced the number of parameters, but the question is that how many parameters we can reduce, or how many parameters can be set equal to 1 through non-dimensionation. Answer is, in this model you have 2 dependent variable n and p and 1 independent variable, that is time. So you can rescale all these variables, and in the original model you can count that there is 6 parameters: r, k, a, b, e, and finally m. 6 parameters, and you have 3 scaling parameters, that is n equal to lambda x, p equal to mu y, and t equal to some eta t rest. So you can choose lambda, mu, eta such that 3 of the coefficients can be make equal to 1. So once they are equal to 1, so then the resulting model will be having 3 parameters. Now I just want to mention that this is not the only possible form of this non-dimensionalized version. If you go through different books and different literatures, you will be finding different types of non-dimensionalized version. Quickly I can give you one hint, that instead of 1 here, you can have beta as this position also, that is also another valid non-dimensionalized version. In some of the paper, especially in the works by Alan Hastings, you can find that this alpha is appearing as a coefficient of x. So that means instead of alpha plus x, most of the times in Hastings paper you can find this is 1 plus alpha x. Another possibility is that you can make this is equal to 1, so this alpha will be involved either as a multiplicative factor here, or this 1 will be replaced by alpha. So there are several types of possibility by which you can choose the non-dimensional scheme such that you will be having different types of non-dimensionalized version. So the non-dimensionalized version is not an unique form, rather you need to non-dimensionalize the model just in order to simplify your algebraic calculation to understand stability and bifurcation behavior, but there is no unique way. But you need to keep in mind, or you need to set your goal, that which phenomena or which characteristics of the given model you are interested to judge, that how it affects the dynamics of the system. So accordingly you need to finalize that, okay, this is my non-dimensionalized version. Now from this equation, quickly I can give you the idea how you can ensure that solutions remains positive if you start from any positive initial condition. You can verify that you can write x equal to some x into f1 xy, you can take x common, and similarly you can write y dot equal to y times some f2 x comma y, and if you solve this equation from 0 to t, so then you will be having xt, that is equal to x0 times exponential integral 0 to t f1 xs ys ds. So the factor multiplied with x is a continuous function of x and y, and therefore it is a continuous function of s. So therefore this exists, right? In other words, this is Riemann integrable, and therefore if you start from a positive initial condition, due to presence of exponential function, the solution will remain always non-negative. It might be approaching to 0, asymptotically it can converge to 0, but it should not be a negative function of t because exponential term is present here and you are choosing x0 as a non-negative quantity. The similar conclusion holds for y also. Now for this model, if you now calculate the equilibrium points and other stuff, so you can find there is 3 equilibrium points. 3 equilibrium points are of the form E0, that is 0, 0, then E1, 1, 0, and E star, that is x star, y star. And these x star, y star, they are positive solutions of these two equations. This is equal to 0 and beta x by alpha plus x minus delta, this is equal to 0. So we can say that this interior equilibrium point is the points of intersection of these two curves in the interior of the first quadrant. So now if you solve the second equation, from here you can calculate x star is equal to alpha delta divided by beta minus delta. As we have assumed all the parameters are positive, so therefore alpha, beta, delta are all positive. But for feasible existence of x star, we need this parametric restriction, that is beta should be greater than delta, right. Similarly, if you substitute this x star here, then you will be having y star, this is given by 1 minus x star into alpha plus x star, correct. Now this parametric restriction ensures positivity of x star. For the positivity of y star, we need that x star should be less than 1, right, because alpha is positive. So once x star is positive, this y star will be positive whenever x star is less than 1, and if you substitute this expression here, that is alpha delta by beta minus delta here, so that means alpha delta by beta minus delta less than 1. So from here you can find that beta should be greater than delta into 1 plus alpha, correct. So as alpha and delta are both positive, so combining these two restriction, we can say whenever this inequality is satisfied, then interior equilibrium point is feasible. Now geometrically what we are having here, if you plot this curve in xy plane, you will be having a curve like this, that is a parabola. In this axis x, here you have y, and this is the plot for 1 minus x equal to y by alpha plus x. And second one, that is if you plot this particular equation, this will be a straight line. So this is the straight line, that is x star is equal to alpha delta by beta minus delta. Now if you choose any one of them as parameter and if you keep on varying them, at a time you choose only one parameter as a variable, then you can see that these positions of the curves will be changing. Now here you should be careful, that is my suggestion, some other people may not be agreed with me, but the point is that I always suggest you choose a parameter in such a way that any one of the curve will be changing its position with the variation of the parameter. So now you can see this alpha is involved with both the equations. So better possibility is that you do not touch alpha for the time being. You choose either beta or delta as parameter which will be varied in order to check the stability of equilibrium, change in stability property of the equilibrium, as well as existence of the equilibrium point. Now you can clearly understand that for this purpose your beta is a most suitable choice. Why? Because if you change beta, so only position of the line will be changing, right? And with the increasing magnitude of beta, what will happen, that this line will be moving along this direction, correct? And you can check that whenever this condition is satisfied, beta greater than this, so what does it mean? It actually comes from this condition x star less than 1, right? So geometrically it means that this vertical straight line lies on the left hand side of 1 0. So once this particular line is on the left hand side of 1 0 and this is a continuous curve, so there should be one point of intersection. So therefore this condition geometrically ensures the existence of a point of intersection within the first quadrant and hence the feasible existence of the equilibrium point. And here you can face one bifurcation, that is when this particular vertical line passes through the point 1, 0, and that particular threshold situation can be obtained as beta equal to this one. Analytically you can prove that whenever beta passes through the value delta into 1 plus alpha from lower to higher, then you observe a transcritical bifurcation here. Right now I can show you that whenever this line lies on the right hand side of the point 1 0, then this is stable, and if x star lies between 0 and 1, then this becomes unstable. And also you can very easily confirm from linear stability analysis that when this 1 0 loses its stability, at the same time this interior equilibrium point becomes stable. Before that, interior equilibrium point is not feasible. Mathematically it exists, but in the context of population dynamics we can say that interior equilibrium point does not exist if beta less than delta into 1 plus alpha, because what will happen, that this line will be intersecting this parabola in the fourth quadrant, so that is not a feasible equilibrium point for the population dynamics model under consideration. So for stability, if you calculate the Jacobian matrix, so Jacobian matrix will be J x comma y, this is equal to 1 minus 2x minus y by alpha plus x xy divided by alpha plus x whole square minus x by alpha plus x. Here you will be having beta y by alpha plus x minus beta xy divided by alpha plus x whole square, and here you will be having beta x by alpha plus x minus delta. This is the Jacobian matrix at a typical point x comma y. Now if you calculate this at origin 0 comma 0, then you will be having 1 0 0 minus delta. Diagonal matrix, this eigenvalue is positive, this is negative, so therefore origin 0 comma 0 is always unstable irrespective of any parametric restriction, and in particular it is a saddle point. It is a saddle point, right? Now you can verify one interesting thing here. You can see that origin is unstable from x direction. This is a diagonal matrix. Eigenvectors are 1 0 and 0 1. 1 0 is involved with the eigenvalue 1 and 0 1 is involved with the eigenvalue minus delta. So that means this origin along x axis it is unstable, but along vertical axis it is stable. Stable means the trajectory if you start from y axis, it will be converging to 0 0. But if you start from any point on x axis, it will be moving away from the origin, and this is in accordance with the model under consideration, because if predator is absent, then this is the simplest logistic model for prey population growth, and you know for prey population growth 0 is unstable, 1 0 is stable equilibrium. So in absence of predator, if you start from a small population density, population will be converging to its carrying capacity, and as it is a specialist prey predator model, predator cannot survive in the absence of prey. So therefore if you start from a point on y axis, it will be converging to 0 0. So that means predator will be going to extinction. Next, if you calculate J1, so that is J evaluated at 1 comma 1, so this will be equal to, sorry, this should be 1 0. This is minus 1, no contribution from here, this is minus 1 by 1 plus alpha, this is equal to 0, and here you will be having beta by 1 plus alpha minus delta. Right. So in this case, stability of 1 comma 0 depends upon sign of this particular quantity. So therefore we can say that 1 comma 0 is stable if beta by 1 plus alpha less than delta, and this is unstable if beta by 1 plus alpha is greater than delta. And now you can verify that beta greater than delta into 1 plus alpha is the parametric restrictions required for the feasible existence of x star y star, and under this restriction this 1 0 is unstable. So therefore whenever interior equilibrium point exists, then 1 0 is unstable. On the other hand, if beta less than delta times 1 plus alpha, then this 1 0 is stable, there is no interior equilibrium point, origin is a saddle point. So if you start from any initial prey and predator population density, predator population will be going to extinction and prey will survive at its carrying capacity. So this is the idea. Finally, when we are interested to find out the stability of interior equilibrium point, the calculation is little bit tedious, but I can show you a particular tricks by which you can calculate J x star y star easily. We are just going to utilize these two equations, because common solution of these two equations will give you the x star y star. So we can say that this is equal to 0, this is equal to 0. Now first of all you can calculate A12, this will be simply x star by alpha plus x star, then A21, this will be equal to alpha beta x star y star divided by alpha plus x star whole square, right. I am not going to simplify them, and A22, this is equal to 0 due to this condition. Now once you have these quantities in your hand, immediately you can calculate the determinant of J star, this is greater than 0. Why? Because your A22 is 0, so this product is 0, minus A12 into A21, A21 positive, A12 negative, so therefore determinant is positive. So the second condition for stability is already satisfied whenever your x star y star is feasible. So then we need to verify whether trace is negative or not. Now in order to calculate trace, then trace of J star, this is nothing but this expression, that is 1 minus 2 x star minus y star by alpha plus x star plus x star y star divided by alpha plus x star, this whole square, and we can reduce this expression step by step. First of all, you can take help of this result. So with this one, from this part you will be having only minus x star. Then from here you can write x star by alpha plus x star is equal to delta by beta. So therefore this will be equal to plus delta by beta y star divided by alpha plus x star. And again from this relation you can write y star by alpha plus x star equal to 1 minus x star. So therefore you will be having minus x star plus delta by beta times 1 minus 1 minus x star, right. And in this expression if you substitute the expressions for x star, I am not taking, I will not be taking much time, but I can just directly write down this expression. This will be delta by beta times 1 minus beta plus delta divided by beta minus delta, this multiplied with alpha, right. Now from here, once you have this particular expression, so then you can demand that if trace of J star less than 0, then you will be having E star as stable equilibrium point, otherwise it is unstable. So what is the stability condition? Stability condition is 1 minus beta plus delta by beta minus delta alpha, this is less than 0, implies alpha should be greater than beta minus delta divided by beta plus delta. Now finally I will give you an interesting idea that by chance if you make this quantity equal to 1, right, it may not be possible to derive the existence of oscillatory condition. That means instability through Hopf bifurcation. Why? Because if you solve this inequality for beta, so what you will be having, that beta should be less than alpha plus 1 by alpha minus 1 into delta. So if you solve this inequality for beta, then you will be having that beta should be less than alpha times 1 plus delta, 1 minus 1 plus alpha by 1 minus alpha. So if your alpha equal to 1, so this quantity is undefined. And actually if you consider alpha here, this alpha is somehow related to the position of the vertex of the parabola. So in order to have the Hopf bifurcation, you need to choose appropriate value of alpha. So what is the Hopf bifurcation here? Hopf bifurcation is given by the condition alpha equal to beta minus delta by beta plus delta. Because if you choose alpha as a parameter, then you need to choose some particular values for beta and delta, and as alpha is a free parameter, it might be greater than this quantity or less than this one. So if you vary alpha continuously, so there will be a threshold for alpha that is denoted by alpha equivalent to alpha h, and its expression is beta minus delta divided by beta plus delta. At this situation you will be having trace of J star is equal to 0, right. So once your trace of J star is equal to 0, then for Jacobian matrix evaluated at E star lambda 1 comma 2, this will be equal to plus minus root over minus 4 determinant of J star divided by 2, because your trace is 0. So that means you are having complex conjugate eigenvalues, call it plus minus I omega, because whenever your x star y star is feasible, then determinant is positive. Once determinant is positive, so therefore it will give you a complex conjugate eigenvalue, and from continuity, from the continuity of the expression in terms of alpha, we can assure that eigenvalues are of the form, say, mu plus minus I omega for general alpha. So that means we can say lambda 1 comma 2, they are functions of alpha, so that is lambda 1 alpha and lambda 2 alpha, and this will be equal to mu alpha plus minus I omega alpha, and in particular at alpha equal to alpha h, what you have, that mu of alpha h, this is equal to 0, and omega alpha h, this is greater than 0, right. So therefore we can mention here the condition required for Hopf bifurcation demands satisfaction of 3 conditions. That means if you have J star as the Jacobian matrix and consider this as a function of alpha, so for Hopf bifurcation in 2 dimension you need this condition, that number 1, trace of J star evaluated at alpha equal to alpha h, this should be equal to 0. Number 2, determinant of J star evaluated at alpha equal to alpha h, this should be greater than 0. And number 3, that dd alpha, or you can write del del alpha, but as we are considering other parameters are constant, so therefore this trace of J star at alpha equal to alpha h, this is not equal to 0. So these 2 conditions ensures the existence of complex conjugate eigenvalue at alpha equal to alpha h, and this is some sort of transversality condition. It ensures that real part of the eigenvalue is not only passing through the value 0, rather it crosses the axis. So because if we demand that trace of J star equal to 0 at alpha equal to alpha h, it may happen that your real part is something like this. So before alpha equal to alpha h it is positive, after alpha equal to alpha h it is positive, or it may be some format like this. So in this case there is no change in sign of the real part of the eigenvalue. So for a change in the real part of eigenvalue, what we need, that this particular function mu alpha as a function of alpha should intersect the this axis transversally, and this is the condition for transversal intersection. And in case of Hopf bifurcation, what you will be having? You will be having some limit cycle. In some of the book you can find that for alpha greater than alpha h there is a limit cycle, but I cannot mention that thing here because you do not know whether this real part will be positive for alpha less than alpha h or alpha greater than alpha h. But we can say in the vicinity of the Hopf bifurcation threshold we can have limit cycle, so leading to oscillatory behavior in the population density with the advancement of time, right. And there are 2 different aspects, that this limit cycle arising through Hopf bifurcation may be stable, may be unstable. So the idea is that you might be having that limit cycle, it attracts all nearby trajectories which are starting either from inside of the limit cycle as well as from the outside of the limit cycle. And if this limit cycle repels all the nearby trajectories, then it is an unstable limit cycle. And accordingly, the Hopf bifurcation is known as supercritical Hopf bifurcation and subcritical Hopf bifurcation. So, the idea is that if we just try to summarize all the result, so if your beta is less than delta into 1 plus alpha, then predator population will be going to extinction. Then for beta greater than delta into 1 plus alpha, you have coexisting equilibrium point. This coexisting equilibrium point will be stable if your alpha less than alpha h or greater than alpha h, that you can derive, and at alpha equal to alpha h it loses its stability and leads to some oscillation in both the population. And if you just want to have a rough sketch of the phase portrait for 3 different situations, then you will be having 3 types of phase portrait. In first case, when 1 0 is stable, then you can see all the trajectories, they are converging to this equilibrium point 1 comma 0, this one, this is in this direction, this is in this direction, and this is in this direction. So, this is x axis, this is y axis, 1 comma 0 this is stable, and 0 comma 0 this is a saddle point. So, nearby you will be having trajectory like this. Then once you have this coexisting equilibrium point, so if we consider this is the pre-null-cline, this is the predator null-cline, then if it is stable, either you will be having this kind of phase portrait, that means monotone convergence to the coexisting equilibrium point, or you will be having some sort of phase portrait like this, the trajectory will be converging to this in a spiral way. And once you are able to find out a threshold such that the nature of the eigenvalue changes from 2 negative real eigenvalues to 2 complex conjugate eigenvalues with negative real parts, then phase portrait will change from this type of phase portrait to this one. And at the threshold where this eigenvalues changes from negative real numbers to complex conjugate eigenvalues with negative real part, that is known as loss of monotonicity property. Why? Because in this case all the trajectories are monotonically converging to the equilibrium point. Here trajectories are converging to the equilibrium point, but their convergence is not monotonic. So, there will be some sort of damping in the advancement of the time series with time t, and ultimately it will converge to the equilibrium point. And beyond Hopf bifurcation threshold, that is whenever your pre-null-cline something like this, predator null-cline is something like this, so then you will be having some stable limit cycle here, and you can see all other trajectories, they are converging to this limit cycle from inside as well as from outside. So, these 4 types of phase portrait you can have from this particular system. So, in this case predator goes to extinction. In all 3 cases you will be having prey and predator both survive. Here their coexistence is stable, and here their coexistence is oscillatory. And you can just observe that whenever we have this limit cycle, I plotted this vertical null-cline in a particular position, that is this vertical null-cline lies on the left hand side of the maximum of this parabola, and geometrically you can verify that the Hopf bifurcation threshold, that is alpha equal to that beta plus delta by beta minus delta, that is the condition that this line passes through the vertex of the parabola. So if you calculate the vertex of the parabola and find the condition that this line passes through the vertex of the parabola, then you can prove that that parametric restriction is same as alpha equal to beta plus delta by beta minus delta. So geometrically in this case we can say that if this vertical line lies on the left hand side of maximum of this parabola, then this equilibrium point is unstable. If it lies on the right hand side of this particular vertex, then it is stable, right. Finally, I just mention 2-3 different types of functional response. Those are also involved with the Gause type of pre-predator model. You can have type 3 functional response. This type 3 functional response is given by Gn, this is equal to alpha n square by beta plus n square. In this case, if you draw a sketch of this particular function Gn, then you can find that it will be a curve like this, S-shaped curve. You can find that at initial stage, this growth is not that much sharp compared to the Holing type 2 functional response. In between, you will be having a point of inflection. After that, it becomes saturated. So this type of functional response is most of the time applicable for interaction among autotroph and herbivore. In case of autotroph herbivore interaction, that means grazing of autotroph by herbivore, most of the time follows this kind of sigmoidal functional response. There is another functional response that is sometimes called type 4 functional response, but of course there are some other type of formulations from which you can have the similar kind of behavior, where type 4 functional response is of the form that is Bn divided by n square by a plus n plus c. In this case, if you plot the function, it will be a function like this. This is n and this is Gn. Of course, this curvature, existence of point of inflection, this vertex, that means its height, sorry, not vertex, this is the height of the maximum and its positions, they are actually determined by these 3 parameters. And of course, this type of structure can be also captured by Monod-Haldane type functional response, which is given by Gn, this is equal to alpha n by some beta square plus n square. This also produces this type of structure. And finally, I just mentioned that this is not the general idea that all the time functional response should be a function of prey population only. Rather, if we assume that functional response is a function of prey population only, so this is again another special class of prey predator model that is known as prey dependent functional response.
So your type 3 function says I should have a minimum prey population for the predator to start feeding.
No. In this case, the idea is that amount of grazing is not that much sharp when availability of n is relatively low, right, because here slope is something like this one, but in case of Holing type 2, slope is like something like this one. In both these cases, you are having this type of local maximum and ultimately it is going to 0 as it tends to infinity. So this is also known as some sort of crowding effect. that when the group of prey individuals is very large, then predator face some tough time to catch a single prey. Then they are looking for some lonely juvenile prey or little bit weak prey as their easy capture. And there are some other type of functional responses. One such
type 4 functional response is not widely used because so far whatever I study, people stop with type 3 functional response. So why is this type 4 functional response?
This type 4 functional response, there is a series of paper by Ulkovich and his collaborators, and monod type functional response is also used in case of some phytoplankton zooplankton interaction, specifically in case of toxic phytoplankton. So what will happen, that if the concentration of phytoplankton is very high and they are toxic in nature, then zooplankton always try to avoid the dense assemblage of the toxic phytoplankton. So therefore grazing of that toxic phytoplankton by the zooplankton reduces at higher concentration of toxic phytoplankton species. So that's why they uses this kind of functional response. And most of the time people avoid to consider this type of format only for the reason because its dynamics is quite complex. And another thing is that it shows some sort of global bifurcation scenario. Because in this case, if you proceed with this type of functional response, then you can recall that in order to find out the component of x star, you will be having a quadratic equation. So once you will be having a quadratic equation, so under certain parametric restrictions, you will be having two coexisting equilibrium point. And once you have two coexisting equilibrium point and one of them is destabilized through Hopf bifurcation and the size of limit cycle keep on increasing with the change of the parameter value, at certain time point it will intersect or it will collide with the second equilibrium, leading to homoclinic bifurcation. And this homoclinic bifurcation is also known as some sort of catastrophic change in some context. Then people have some sort of objection that in this model I can't see any catastrophic change. But that can be justified in a different way. Okay, that mathematically I can vary the parameter from this point to that point. But for a particular species, their grazing rate, their death rate, environmental capacity may not be varying with such a large range. So therefore dynamics, what we are getting here by studying a particular model, that is some sort of library. If you can identify an interacting population model and mention that okay, I suspect that time evolution or time series I am having for this interacting species is more or less matching with the observed phenomena for this model under consideration, then you can estimate the parameter and try to fit with the model. There might be a good fit, there might not be. So depending upon the exposed discrepancy, you can change your modeling approach. And the most important part is that most of the time we cannot ensure that which modeling approach is most suitable for the system under consideration. Once you consider ODE model, then people can ask the question why you are not considering the movement of the individual within their habitat. Then you need to move on to PDE model. Another one can ask the question why you are not considering variability of the parameters with the change in environmental condition. So that will be a non-autonomous model. Next question may come up that why you are not considering random environmental driving forces or fluctuation in your modeling approach. Then stochastic differential equation will be coming into picture and so on, due differential equation, etc., etc. And frankly speaking, that this type of model is valid only for some isolated species. But most of the time they have several connection to other resources and other predators. So mathematical model is just to simplify the dynamics and try to have an understanding of the system behavior. So finally, I like to make one comment that there are certain other type of functional response, that is Bedington de-Angelis functional response or ratio dependent functional response, where functional response is a function of both prey and predator density, and those are actually called predator interference to the predation. Because if you have very less amount of prey and large predator density, so then they will be interfering among themselves in order to catch their prey. So that type of interference can again reduce the grazing pressure on the prey population. So those are also available in the literature. And whatever I have covered so far in last 3 lectures, that means 3, 4 and 5, you can look at the book by either J.D. Murray or Marcotte. Title of the J.D. Murray's book is Mathematical Biology, Volume 1, Volume 2. You will find all these ODE models in Volume 1, and Elements of Mathematical Ecology by Marcotte for this kind of discussion, phase portrait, other related things, and mainly special emphasis on dynamics of a model with this type 4 functional response. Right? So you can stop it here.